Hey guys, this is the notes for a lot of 2.1 day 1. We got through some of it. I would like to have you, before we start, you should take out that kind of, I guess you'd call it a poster we made in class on Friday, where we kind of made an enlarged version of this graph. So I'm going to just talk about it again. This in here is a little review, but I want to go down to the bottom where we were talking about as you make the h, or the delta x, or change in x, smaller and smaller. And again, some books use h, some use change in x or delta x for the change in x, and it really doesn't matter, it's just notation, but kind of know this is a change along the x-axis. The slope of the secant line as compared to the slope of the tangent line becomes the tangent line gets really close to that slope of the secant line. So if we can make h smaller and smaller and smaller and smaller as we calculate the secant line, which we talked about how that's the limit, we'll get a really good answer for the tangent line. And we said although you can't make h 0 because in our difference quotient that h is on the bottom, we can't divide by 0, we can get really close. And again, we talked on Friday about how that means we can take a limit as we approach as we approach 0. This limit is called the derivative. So this is where we left off on Friday, where we had said that the slope of my tangent line, which is really called the derivative of the function, again this is just notation, is equal to the limit as I get closer and closer and have my change in x become really close to 0, is really close to the slope of the secant line. And remember, slope was change in y, and we did this all on Friday, so unless you were absent, you should be going, yeah, she already did this. Alright, so this is really key, that when you're finding the derivative of a function, you're really finding the slope of the tangent line. And to do that, we find the slope of the secant line, and we just keep pressing it closer and closer and closer until it becomes almost right on top of that tangent line. So on the next page here, now you should have your notes out. The other stuff we'd already talked about. So when you're being asked to find the derivative, you are really being asked to find the slope of the tangent line. So let's go ahead and write that. Slope of the tangent line to a point on a curve, right? Which is really going to be, and again, this is the third time I've said it, the limit. And it's the limit as the change in x. Now I'm going to repeat myself again, which we're calling h, or you might see it written as delta x, becomes very close to 0. So this is a very key point right here. My derivative, and it's the third time I've written it, so you can tell how important I think this is the limit as that change in x, or that h becomes close to 0, of the slope of the secant line. And again, our derivative is really just a word given to the slope of the tangent line. These are two equivalent phrases. There are several different notations or symbols that we can use for the derivative. Some are used more than others, but I'm going to put them all down here, and I think I'm going to put them down in the order that we're going to use them. So if the function were of the form y equals, then we call the derivative of the function y with this little line, and we read that as y prime. All right? If the function is given in the form f of x equals, then we say the derivative we call f prime of x. All right? Those are used, you'll see us use those interchangeably. They both mean to find the derivative of the function. The other ones we're going to use, I'm going to move over here so I don't run into that text up above. When we see dy dx, this means the derivative of y with respect to x. All right, so dy dx is also telling you to find a derivative. Sometimes instead of a y right here, it'll be df of x, because y equals f of x, dx. That also means find the derivative. And the one we see the least is a big capital D, like this. Okay? So all of these are notation for finding the derivative. Their use depends on kind of what text you're using and what form the original function's given in. But if you see this, it means find the derivative, find the derivative, find the derivative, find the derivative, and find the derivative. All right, so finding the derivative using the definition in that box is called using the limit process. So if it says find the derivative using the limit process, that means this way. Because we're going to have another way that you're going to like a lot better, but we need to understand this way first. So before I give you all the little shortcuts and easier ways. So it's called the limit process, or using the definition of the derivative. All right, so both of these, when it says you have to use the limit process or the definition of the derivative, you must take this route. The rest of the chapter actually is going to be devoted by could we get around using this route. And so a lot of the time, you're not going to be asked this outside of this part of this section. You might see this once on a test and one problem on a quiz, but you do need to know how to do it, and it's the understanding behind it that's really important, not the process itself. So I'm going to find the derivative of this function. Now, you should be really familiar with this function. I'm going to go kind of give you a little sketch over here. It's that parent function of a parabola going right like this. So there's my f of x or y equals x squared. And it says I'm supposed to find the derivative using that limit process. I would not memorize that process. I would kind of get used to thinking it through the way we made that poster in class. That at this point I've got some value x and f of x. And at another point on here that I move over a tiny little bit that we're calling h or delta x, but I'm going to use h for today. We've moved over h on the x-axis, and then we'll find the y value at that new x value. So right here is that secant line, and we're in search of the derivative, which is the slope of this green one, or this tangent line. So what we do is we take this secant line and we find its slope. We do change in y over change in x. So I'm going to write that down. Again, I'm not even going to use this function quite yet. So let's write that down. We do f of x plus h minus f of x, change in y, subtract them, over change in x. So I'm going to do x plus h minus x. And that gives me just that h on the bottom, which you saw up here in this difference quotient up here, up on the top of your notes. Now, that's going to give me the slope of the secant line. I don't want that. So what I do is I take and I move that secant line. I get it closer and closer and closer. So really what I'm doing is I'm pulling h in closer and closer. So I'm taking the limit as h approaches 0. All right, so really what I've got here is that's how I get my derivative. And because this is written as f, usually you'll see then your derivative using the f prime notation right here. Had it been y equals, we'd probably use this one, or maybe dy dx. But it's all means find the derivative. I would like you to write this down every time you do one of these for the first few assignments. So now we're actually going to go find this. All right, so I'm going to extend my page here, get me a little more room. There we go. So let's go find that derivative. Here's what I've got. F of x equals x squared. So remember that. That was my original function. So let's go find my derivative. My derivative of the function at any point, again, I just randomly put one right here, but it means a derivative at any point. My derivative of f at x is equal to my limit as that change in x gets closer and closer to 0 of f of x plus h. Well, that's going to be x plus h squared minus f of x. Well, when I put an x in, it'd be x squared all over h. So now what I do is I need to use my algebra skills. I'm going to FOIL that top out. So when I FOIL that, maybe off to the side here, x plus h times x plus h gives me x squared plus 1xh plus 1xh, so plus 2xh plus h squared. You might want to, keep some of that stuff off to the side. So I'm going to have x squared plus 2xh plus h squared minus x squared. Again, all I did to get this part of it right here was FOIL that all over h. And this is a limit, and again, direct substitution fails you here because you're going to get a 0 over 0, but the whole goal is we're going to try to get that h to cancel. That's going to kind of be in the back of your head. Ultimately, we want h to cancel. Right now, x squareds go. So I have my limit as h approaches 0 of 2xh plus h squared all over h. And you can see on the top here now I can factor out an h, which I'm going to do right now. So I've got my limit as h is approaching 0. I'm going to factor out an h, which is going to leave me 2x plus h all over h. And these cancel, so now I can do my direct substitution. So it's going to be my limit as h approaches 0 of just 2x plus h. And at 0, this is just 2x. So this is the derivative of my function at any point can be found by doing twice the x value. Now, that's pretty abstract right now without a graph. So I want to show you graphically what that means. So I'm going to bring up my TI-82 calculator, or 84 calculator here in a second, just to show you what's going to happen with this. But we'll go do a graph by hand. So when we're doing the graph of y equals x squared, here parent function, let's go whip that on up there. Should go through 2.4 actually if I'm going to be real picky. So this was my graph of f of x or y equals x squared. And I'm saying that the derivative at any point is twice x. Well, that graph looks like a line through 0, 0, 1, 2, 2, 4, negative 1, negative 2, and it looks like this. But understand what this function is giving you. It's giving you the slope of the tangent line at each of these points. It's saying that the slope of the tangent line right here, where x is equal to 1, is 2. Okay? Which makes sense. The slope of the, you can see at 1 over, I'm 2 up. So this is the graph that gives you the slope of the tangent lines at each of those points. Still kind of abstract, but let's answer. I'm going to put it up on the TI-84 and discuss this on your graphing calculator, and I think it'll tie it all in. So this is, what is the slope of the tangent line when x equals 4? Well, right here, we said that f of x, its derivative, was twice x. We just went through a whole process of it. So it's 2 times 4, which is 8. What does that mean in terms of the graph? It means at 4, the slope of this line is really steep. It's actually 8. How about when x is 0? Well, it's twice 0 is my derivative, which is 0. That should make sense to you. And here's my point. At 0, the slope, oops, sorry, moving the line around. At 0, the slope was 0. But look right here on the original function. At 0, the tangent line is horizontal, and it has a slope of 0. So that all ties in. So down on the bottom, what I really want to talk about next is, well, how do we do this on the graphing calculator? I hope I have time here. I do. I have a minute and a half, so I'm going to have to go into another video, but I'm going to get the graphing calculator part of this done. So I'm going to pop up my graphing calculator. There it is. And I'm going to take our original function, which was f of x equals x, equals x, let's clear that, x squared. And you know that's a parabola, but I'm going to go graph it anyway. I'm going to go take a look at the graph, and I'm going to go to the large screen here, and hopefully you can see most of the graph anyway. And there's a function on your calculator that's called the dy dx function. And dy dx is just one of those notations I gave you for the derivative. So when I go to my second calc option here, second calc, let's see if it'll do it. I think I hit trace. Come on, second calc. It's being fussy. There we go. If you look at the sixth option down here, it says dy dx. What that is it calculates your